All right, thanks, Mean. Hi, my name is Tej. I'm going to talk about verifying code written in Go using calc. So broadly speaking, when we do systems verification, we have an implementation and we have a specification. I'm using blue to indicate the implementation language and this pale yellow to indicate calc. And we want to connect the specification to the implementation somehow using a proof. Now, of course, we can't do that directly. We have to somehow take the implementation and connect it to a model inside calc in order to actually carry out this verification. And this connection between the implementation and the model is the focus of this talk. In our previous work at SOSP, as well as our current work, we focus mostly on the proof aspects. But here I'm just going to talk about how do we connect an implementation to a model. Okay, so my research group, PDOS, we aim to verify realistic systems. So when we say systems, we mean, first of all, it definitely needs to have running code, and it needs to interact with the outside world in some way. So that means we talk to disks, we talk to networks, somehow it needs to produce a visible effect. We also want realistic systems. We want them to be reasonably efficient. That doesn't necessarily mean competitive with existing implementations, but reasonable. And lately, realistic has also meant concurrency. When we say verification, we generally verify full functional correctness, but we have an extra focus on crash safety. So we develop a lot of storage systems, and we prove that they store your data safely, even if your computer crashes at any time. The reason why I mention this is because this need for crash safety research means that we need a lot of flexibility when actually doing the verification. We're also developing new verification tools. So our goal when doing the system verification is we want to write the code in an actual systems language, as opposed to, say, extracting from something written in calc. We want to write ordinary code, import it into calc, and then prove something on top of that model. And concretely in this talk, I'm going to talk about a system called Goose. Goose supports writing code in Go and verifying it in calc using Iris. So why Go? Go is simple, and it has good tooling. And when I say good tooling, I mean in two dimensions. So first, it has good tooling for actually writing the code. We can test it, we can profile it, we can make it faster. And second, it has good tooling for parsing, for actually developing this tooling that translates Go to calc. Why Iris? Iris has fantastic support for concurrency, and it's highly extensible. So we can build new verification techniques on top of Iris. I think much of this could be done in VST in principle, but we don't have any VST expertise on our team. Okay, so why do we want to write code in Go? So just to emphasize this point, Go gives us all this tooling for non-verification related activities that actually let us write the code. And not just write the code, but also make it fast enough. So we can test it, we can debug it, we can profile it. It has good concurrent profiling tools as well. We can benchmark it. And only when we're reasonably confident that we have fast code and that it is maybe correct, do we start doing verification. Okay, so the contribution of our work here is Goose, which is an approach for importing a subset of Go into a model inside calc. What does this subset include? So Goose includes all the basics you need for concurrent systems programming. We have locks, we can fork off threads, we have structs and pointers. One feature we don't currently support is Go's interfaces. Interfaces are Go's support for dynamically typed values. But it's enough of Go to write concurrent systems code. We have a translator. It converts this code into something in calc. So what do we actually produce in calc? We produce a program in GooseLang. GooseLang is a copy-paste of heaplang, if you're familiar with that. It's also similar to lambda Rust, if you've heard of that from the Rust Belt project. GooseLang is a lambda calculus with references and concurrency, and has some extra support on top of that is different from both heaplang and lambda Rust, because we need some external operations. So basically, you can think of this as system calls. In our current work, we're doing file system verification, and those extra system calls allow us to read and write to the disk. Okay, and I've also drawn a smaller box inside GooseLang, which is the target of the translator. This is because GooseLang has features which are not accessible from Go. It's a more general language. This is handy because it means that we can support features, we can gradually support more and more features of Go by using the extra functionality of GooseLang without making drastic modifications. And then GooseLang plugs into Iris. So Iris allows you to bring your own programming language. and then it gives you a weakest precondition calculus over that language. And GooseLang just directly implements what Iris expects, which should come as no surprise since it's a copy-paste of heaplang. Okay, so we've already been using Goose. We wrote a persistent key value store, but then this turned out to be quite hard to verify. So we did a simpler example for a paper we published at SOSP, which is a concurrent mail server. Now we're switching to something that is more realistic. It's a much larger program. So the mail server is like 150 lines of Go code. This file system is currently 3,000 lines of code. So we're working on doing this, and we're hoping to verify this file system. So the file system is basically written, but we don't have a proof yet. So Go, you maybe are not familiar with Go. Go is a systems language. It's C-like. It has functions and structs and pointers. It's garbage collected, which is convenient when you're writing code, especially concurrent code. It was originally designed as a systems language as a replacement for C. And so it exposes system calls. It has good access to C functions. This is good because we sort of need direct access to the system, and we need to make assumptions about what those system calls do. So it's best if it's as low level as possible, so we're not making assumptions about more code. Go also has an efficient runtime, so we have a good garbage collector. The threading support is very efficient. Here I'm mostly contrasting with Haskell. We've done work with concurrent Haskell where the runtime was not nearly as fast as Go. What is Goose code? So Goose is a subset of Go. It looks like standard Go, but we mostly have to avoid the standard library. This is because we're going to verify all the code, so it makes sense to avoid these extra standard library features that we don't want to model. It does provide some narrow interfaces for interacting with the file system or the disk as external operations. Mostly you can think about the disk as being the external operations because now we're doing file system verification. And it's a very simple API. I'll give an example later. And over time, Goose is growing to support more and more of Go. It's fairly easy to add features. So the bulk of this talk, I'll focus on two challenges in implementing this whole approach. The first, more interesting aspect perhaps, is GooseLang, which is the semantic model of Go. And then I'll touch on some aspects of the translation process after talking about GooseLang. Okay, so GooseLang is, as I said, it's a lambda calculus. It has references for modeling the heap, and it has concurrency. And then, so this is so far heaplang. Then we extend it with an extra operation call, which calls some external operations. And GooseLang is parameterized over what these external operations do. That means what operations do you have, what is their semantics, and also what state do they manipulate in the semantics. So the disk and the file system clearly have very different state. What do values look like in this language? We have standard sums and products like heaplang. We did make one change, which is that numbers are represented as actual proper 64-bit numbers. And we also have 32 and 8-bit numbers. This location constructor is used for memory addresses. You can think of it as being analogous to a Go pointer. The GooseLang language has pointer arithmetic, but Go does not have pointer arithmetic. We use this pointer arithmetic to model arrays, as well as access to field elements inside a struct. Okay, so here's an example of something that is in GooseLang. So again, I'm using this yellow color for calc. So this is all code written inside calc as part of GooseLang. Here I'm giving the model of slices. So slices in Go are a combination of a pointer and a length. And our model inside GooseLang is very similar. It's just a tuple that has these two elements. And we can write code to model the primitives of Go. So this makes GooseLang a bit of a shallow embedding. So even though it is a deeply embedded AST, we have shallow features like this. So slice append, it appends one element to a slice. We model it as a calc level definition, very much like you would do standardly in heaplang. It allocates a new array that's one bigger, it fills it in, and then it returns a new slice, which is again a tuple of two elements. So what does this look like on the Go side? So one way you might use this is you might index into a slice, and the model for that is we just load a field after doing some pointer arithmetic, and you might append, and again that translates to this function that we've written in GooseLang. Loads are a little bit more complicated than what's on the slide. In reality, Go will panic. It will throw an exception essentially if this index is out of bounds. And our model does account for that. It has undefined behavior if that index is out of bounds according to the length. So concurrency is the more interesting aspect of GooseLang. So here's an example of a concurrent program. So this is sort of a translation of the non-deterministic coin example from Iris, except that we're using a lock to protect it. So what the example does is it allocates this reference x to a bool. That bool starts out false. And then we race between reading it and writing true to it and then return the final value. And this is going to produce true or false non-deterministically. So what does this translate to? I'll highlight some interesting aspects of the translation. So the first aspect that I want to highlight is that this whole new sync mutex call is a primitive that we support with a model of locks. And the model of locks is actually just a spin lock implementation in GooseLang. It's not that Go's mutexes are not literally spin locks, but spin locks are still an accurate model of how locks work. It has the right blocking behavior. Another thing that we had to do is Go does have a definition of the 0 value for every type. And so we had to have at least a basic model of Go's types inside GooseLang, and we need to be able to compute their 0 values, including for strums. And finally, we translate Go's support for concurrency. So the basic way to create concurrency in Go is this Go statement, which launches a user level thread. And that just translates directly to a fork call. Okay, one challenge in modeling GooseLang, which was required an interesting semantic model, is weak memory. So to illustrate this problem, I've given an example of a function in Go, which is valid and has some behaviors, and then here's the translation. So for this purpose of this slide, imagine that our GooseLang language has sequential consistency. It turns out that this will not be the case, but just imagine that's sequentially consistent, and imagine that Go has x86 TSO behaviors and nothing more. Again, Go is a little bit more complicated than that, but this will turn out not to matter. So imagine that we run this program and we see set x, so the forked thread ran first. So sequential consistency on the right-hand side means that if we saw the set x, then the write made it to memory, and therefore we must see x equals 1. Sequential consistency guarantees this is the only execution, given that we saw set x. But on TSO, we can see x equals 0. That store could be buffered on another core, and then we might not observe it in the main thread. So this is bad. The Go program has some behavior, and our model does not exhibit this behavior. So the way we deal with this is we get rid of sequential consistency, and we just make racy loads and stores undefined behavior all the time. The way we do that is we track in-progress stores by splitting stores into a begin and a finish. And then whenever you see that a store has been started in a concurrent load or store, the whole program just has undefined behavior. So that seems bad. So this seems bad. This seems like it should have some ill effect on doing proofs. So I'll make a little detour into how we do proofs in GooseLang. So as I said, we plug GooseLang into Iris. If you're not familiar with Iris, I won't use very much of Iris. It's a concurrent separation logic with higher order Go state. The only really relevant point is going to be the separation logic aspect. Iris is great. It's extremely productive. I'd like to make a plug for Iris. The Iris proof mode is great for doing interactive proofs and is very productive. And also, we can do things like connect to our unwritten POPL 2021 paper, which gives extra support for crash safety, which is something that I think would be unimaginable in some other framework. So why does this work out? Why does this non-atomic stores work out? So we're able to prove Hoare triples for loads and stores, which look like the standard ones. So you have this points to fact, and stores just update the points to fact. The reason why this works out is because P points to V in concurrent separation logic represents exclusive access to P. You can think of it as being ownership of the current thread. And how do we get that exclusion? We either exclude other threads using locks, so we protect this address with the lock before we do loads and stores, or much more common than that is that the pointer is actually fully local. So if you allocate a pointer, the thread that allocated the pointer has exclusive access until it shares. And more often than not, we don't actually share all these pointers. And so we just have full ownership. The only thing you lose is you can't open invariants around this store. But that's fine, that's needed for soundness, and Iris handles that for us. Okay, so one final aspect of the GooseLang model is that, as I said, we can make system calls. And only particular system calls that actually have, that we've given a model. So as an example of that, we have this machine/disk library that wraps accessing a disk. It's actually implemented using the file system, because that's just generally how you do things in Unix. It exports operations called disk.read and disk.write. The blocks are represented as slices of 4096 bytes. And we give that a model inside GooseLang. This is just one example of a set of external operations. And the whole verification project that we're currently doing is to implement a language GooseLang mixed in with file system operations on top of a GooseLang that only has disk operations. And obviously what that means is we take every file system operation and we implement it inside Go, and then therefore we get a GooseLang implementation. One thing that actually I should mention that's interesting here is that the semantics of these external operations actually interacts with the heap, right? You can't make sense of this disk library without knowing that where those pointers come from. You can't use it without having access to Go pointers. So all external operations have to interact with the existing GooseLang semantics. So we also, so far I've just informally talked about the semantics. We give GooseLang a semantics as a standard small step operational semantics over some state. Again, it's basically heaplang, but we have some extra state to track these non-atomic loads and stores. And we also have external state that is manipulated by the semantics of the external operations. One extension that we have to heaplang, which heaplang does not have, is for testing purposes, we have an executable semantics. What that means is we have an interpreter that can run heaplang programs, and then a proof that this interpreter actually produces a valid execution. The interpreter is single-threaded, it only runs one thread, and it fails on fork, but this is good enough to at least test the basic and the core of the semantics, the difficult part. So because the abstract mentions this, I should warn you that what I've been talking about is the current version of Goose, which is quite different from what the submission looked like. Previously, we were using a shallow embedding as the semantic model, but this had some problems. I think I'll skip over what was bad about it. But I'd like to mention that we already have, even now, we still have sort of a shallow embedding. So while we deeply represent things that have to be deeply represented, like heap operations and concurrency, we build data structures out of sums. We don't have a primitive notion of structs, and even something mundane like definition management. So a function is represented as a calc definition, which is also sort of a shallow embedding. So I'll mention a little bit about the Goose translator. The translator is 2,500 lines of Go code. It's implemented in Go because it uses the Go/AST and Go/types packages. These implement a production quality type checker and parser for Go, which is reasonably sound. I think it's not literally, from talking to the Go team, it's not literally the Go type checker, but all the Go static analysis is built on these packages. It's very simple. It's a single pass. It handles each function in isolation. And we can do this because the process is so syntactic and because we have good type information to disambiguate various things. The Goose translator supports a bunch of Go. I won't go into all these features. I think the more important point is that whenever Frans and Nickolai, who are my advisors, write some code that needs more of Go, then usually that gets supported. So definitely on my to-do list is to support multiple packages, probably first-class functions, and probably interfaces. We're not going to support channels because we don't need them. And more sophisticated control flow. So Lambda Rust has some strategy for handling this using CPS. I could do this, but I think this would be a drastic change for very little benefit, so we probably won't do this. To make the translator sound, we have a few tricks. First is just to make it as simple as possible. It's a single pass. You don't have to consider too much contextual information. One other thing is just to make mistakes result in undefined behavior as much as possible. So racy access is an example of this, I would say. Another mistake that you can make is if you just have like random free variables floating around, then generally these will get translated to undefined behavior. one fun thing that I did is I wrote a very basic type system for GooseLang, and then a very basic type checker. The type checker was repeat e constructor. And even this very basic type checker helped catch a bunch of mistakes while initially developing Goose. So things like I was emitting the string TT instead of the representation of unit, the syntax for unit in GooseLang, and this is just, again, some random free variable, which doesn't type check. We also have a testing strategy. Right now, it's basically we have hand-audited integration tests that help prevent bugs when modifying Goose. But we want to extend the testing strategy. I want to touch a little bit on related work. But previously, we used extraction as the workhorse for all of our verification effort. A lot of that was sequential work, and so some of the problems weren't as bad. But basically with extraction, we wrote code in a shallow embedding in this free monad, we extracted it, we interpreted it in Haskell. I think this approach was very productive and it was very easy to get started, but once we started doing concurrency, this just didn't give us enough performance. You have to very tightly control memory usage if you want good performance from concurrent Haskell. I think, as I said, VST and CompCert, I think, could be the basis for this kind of work. I think the flexibility would not be nearly the same that we're getting out of Iris. And again, we have somebody who's an expert in Iris on our team and not an expert in VST. This work is very similar to Rust-Belt in some sense. So similar to Rust-Belt is that Rust-Belt models the core of Rust. It uses a lambda calculus like target, this lambda Rust. And even lambda Rust is quite similar to our GooseLang. The biggest difference is probably that Rust-Belt does not have an automatic translator from Rust to lambda Rust, because that wasn't the focus of the work, whereas for us, this is sort of the point. We need to be able to automatically translate these GooseLang programs would be ridiculous to write by hand. We're actively working on this. So probably the biggest thing is scaling up Goose. We need to handle a very large, a 3,000 line concurrent program that Frans and Nickolai wrote, and they're very intense concurrent hackers. And this program is more efficient. And efficiency means that we handle a lot, we need a lot more sophistication in terms of what Go is being used. Another concurrent project with that is testing. So we want to use this executable semantics to test the translator. So the idea being that you take some programs in Go, you translate them to Coq, and then you compare the behavior of these two implementations. And I think this is basically necessary if you want to gain confidence in a translation process. So to conclude, Goose is a new approach to do concurrent systems verification, where we import Go into a more general model inside Coq. We're actively using it for much of our current verification for, research. And come talk to us. Joe, who's sitting in the back, as well as myself, are at POPL. The code is open source. Feel free to check it out, run it on some Goose programs. And with that, I'm happy to take questions. Thank you.
Okay, thank you, Tej. Questions? Yes.
Thank you very much. Great talk. I have actually a couple of questions, but I will start with one, and then we can see later. So my first question would be something which you didn't touch on in this talk, like a big challenge when scaling up the verification of of code is like also the automation of the proof. Like, what is your strategy there, and what could you quickly maybe talk a bit about that?
Yeah. So we don't have any automation beyond what the Iris proof mode already gives you. So the Iris proof mode makes every step of the proof very high level. I think, and there's some very basic automation for when you apply the load and store rules, let's say. I would say that I think we'll eventually run into this problem, but I actually think that if we need to write one line of code for every line of Go code, that's only 3,000 lines of Coq, which is really not that bad. So I think that won't be a problem. We're not talking about programs that are millions of lines of code.
Okay.
So I was sort of surprised that you say you don't need channels, given that that's a kind of the core concurrency mechanism of Go.
So actually, I disagree with that. I think a big part of Go is to give you support for both of these concurrency mechanisms.
Except channels are built into the language, whereas atomics are like an add-on, right?
So I think mutexes are very much a first-class citizen in Go. So they interact with, they're efficiently implemented, they get to use the scheduler. You couldn't really implement your own mutexes because it wouldn't have good scheduling behavior. I think you might think of our Goose language as being more of the core of concurrent systems, like it's sort of the intersection of all these systems languages, as opposed to being specifically about Go. But yeah, it's a good question.
I was wondering, like, when you translate 150 or 3,000 lines of Go code, how big does the Goose code, like, is it a one-to-one thing, or is your Goose like 10 times as long and you have all these extra administrative instructions everywhere?
I think it's basically one-to-one. We don't really expand. I mean, there are a lot of definitions to make that work, right? So like we call slice append gets translated to slice append, and it's one line of code, but there isn't really any blow up left.
Cool.
So for your executable semantics, you avoided fork.
Yeah.
But in heaplang, at least, there is another source of non-determinism, location allocation.
Yeah.
How do you deal with that? Do you also prove completeness in some form?
No. So we don't have completeness, unfortunately, because we only allocate at one address. I think this is kind of unfortunate, but what it means is that you can't be, if the interpreter fails, you can't be sure that you have undefined behavior. You can never be sure that a program exhibits undefined behavior using the translator, using the interpreter. But you can be sure about any particular execution is a valid execution.
Okay, so yeah, if the interpreter terminates with something, then you know a valid execution exists.
Yes.
And if the interpreter terminates with undefined behavior, then you know there's a bug.
Yeah, I think you don't know there's a bug, but there probably is a bug, and you almost certainly need to fix it. I think in theory you can write weird GooseLang programs that use explicit locations.
Any other question?
So you model the race detector differently from lambda Rust. Why is this the case?
I actually didn't know that lambda Rust does the same sort of race detection, so I think we independently developed this.
Okay, but did you compare the two? Like, I think yours is simpler from what...
Yeah, so definitely we wanted this to be as simple as possible because we're not exploiting these weak memory behaviors. We don't actually have any racy accesses in our code. And so there sort of was no point in being more sophisticated. Go actually does make some vague promises about if you load a pointer that's word sized, you will get some value that was written concurrently. We could model that. But first of all, I also don't want to rely on how Go works. Right? This makes this a little bit more general, so we can more easily transition to some other language. But also, like again, we just don't need the complexity for our actual programs.
Okay, another question, like Rust Belt has like also this goal of modeling, like being a model of the Rust language, and like also like Ralph is working with the Rust people like it. Do you have something similar for Goose? Like, are you working on saying like this is a formal model of Go, or do you just want to write some Go code and verify it?
It's very much the latter. So this helps us develop much faster to not actually have to handle the complexities of Go. So I said Go is simple, and it certainly is, but it's not that there isn't any complexity in Go. There are some things that are definitely tricky, and we don't have to deal with them because we're not actually going to exploit them in our code.
All right, let's thank Tej again.